This video, we're going to talk about 5.3, Objective 3, where we apply and interpret results of the central limit theorem. Start with question 1. IQ scores are normally distributed with a mean of 100 and a standard deviation of 18. Assume that many samples of size n are taken from a large population of people, and the mean IQ score is computed for each sample. If the sample size is 36, find the mean and standard deviation of the distribution of sample means. So the mean of the distribution of sample means remains unchanged. It's the same as the population mean of 100, and the sample standard deviation is going to be that population standard deviation divided by the square root of n. So that's going to be 18 divided by 6. Is going to be 3, and we're going to make this 3.0 as they told us to round to the nearest tenth. Now they ask us if the sample size is now 100. Find the mean and standard deviation of the distribution of sample means. So that mean remains 100, but now we have 18 divided by the square root of 100. It's 18 divided by 10. It's 1 and 8/10. And why is the standard deviation in part A different from the standard deviation in part B? Choose the correct answer below. It is the fact that with larger sample sizes, as in part B, the mean tends to be close, the means tend to be closer together, so they have less variation, which results in a smaller standard deviation. That was answer A. Moving on to number 2, rolling a fair 12-sided die produces a uniformly distributed set of numbers between 1 and 12 with a mean of 6.5 and a standard deviation of 3.452. Assume that n 12-sided dice are rolled many times and the mean of n outcomes is computed each time. Find the mean and standard deviation of the resulting distribution of sample means for n equals 144. So the mean remains unchanged at 6.5. I'm just going to fill that in here as well. Standard deviation is going to be 3.452 divided by the square root of 144. It's 3.452 divided by 12 is 0.2876 repeating. We're going to round that to the nearest thousandth. So that's going to be 0.288. Now we're going to have 3.452 divided by the square root of 81 is 3.452 divided by 9. And that's going to be 0.3835 repeating. And to the nearest thousandth, that's going to be 0.384. And why is the standard deviation in part A different from the standard deviation in part B? With larger sample sizes, as in part A, the mean tends to be closer together, so they have less variation, which results in a smaller standard deviation. This next question is a technology problem. You can see from the dash T here, so we're going to be using the calculator to answer the question. Assume that the population of adults has IQ scores with a mean of 100 and a standard deviation of 15. What percentage of individual adults have IQ scores less than 97? And then part B asks probability that X bar is less than 97. And we need to know here that N is equal to 49 for part B. So let's go ahead and answer that question. And go into the second distribution menu, use normal CDF. We're going to have a lower bound of negative infinity because we're going less than. Second EE 99. Our upper bound is going to be 97. And our mean is going to be 100. And our standard deviation is going to be 15. And this is going to tell us our answer for part A, 42.1%. We'll go to the nearest tenth of a percent. If you're having trouble seeing that as a percentage, multiply that number times 100, round to the nearest tenth. Now we want second distribution, normal CDF, but we're going to take this standard deviation here. We're going to divide it by the square root of 49, which is 7. But we'll just leave it just like that. And we'll find that this changes to be 8.1%. Again, this next one is going to be a technology problem. Assume the population of adults has IQ scores with a mean of 100 and a standard deviation of 15. What percentage of individuals have IQ scores between 95 and 103? And then we're going to change that question to having a average here of sample means between 95 and 103, and n is going to be 100 here. Second distribution 2, and we want 95 to 103, and put that back to 15. First question, and this is going to be 20 point, well, that 9 rounds up to a 10, so 21.0. And then we're going to go back into here, and we're going to divide the standard deviation by the square root of 100. Don't even need to figure that out, even though I know that that's 10. Calculator will figure that out for me, and that changes us to 97.7%. All right. Now we're going to go back to using z-tables to answer this question. So a safety light is designed so that the times between flashes are normally distributed with a mean of 3.00 seconds and a standard deviation of 0.70 seconds. Find the probability that an individual time is greater than 4 seconds. Then part B asks us to find the probability that x bar is greater than 4.00, and n is 50 here. Okay. And then C will answer this question here. So let's change this to a z value. Z is going to be equal to x minus mu over sigma for part A. And for part B, z is equal to x bar minus mu over sigma divided by the square root of n. So 4 minus 3 divided by 0.70. and we're going to round z to 2 decimal places, 1.43. So to find p of z greater than 1.43, I need 1 minus p of z less than 1.43 because my table does less than. So let's find 1.43 on my table. 0, 1, 2, 3, 0.9236. It's 0.0764. And they tell me that it is a little different than that. So let me write what I've got in here. I think their difference is because they used technology instead of the table. So let me check that out. 1.43. Two, and that's 1. And yeah, so they use technology, even though they said to use the Z table here. So let me show you how to get the answer that they got using technology. We'll come in here, second distribution, normal CDF, and my lower bound is going to be 4.00. My upper bound is going to be positive infinity. My mean is 3.00, and my standard deviation is 0.70. I'm going to paste that, and you see that when they rounded to 4 decimal places, they got 6 here. So I'm going to tell you that with this problem that is based off of 5.3.18, when you get that problem in my labs, just go ahead and use technology. So we'll go ahead and just go ahead and use technology for the second part here. And we'll change this sigma to be divided by the square root of n, and n is 50. And we get a very small number here that is a 0 with 23 zeros in front of that 2. So we're going to make this 0.0000, moving around to 4 decimal places. And so now we want to know which of these is more significant. The individual light flashes or the average of 50 light flashes, and the individual light flashes are more important because the times of the single strobe is important. Every single time someone needs to see that, they're not going to see the average of 50 flashes, they're going to see individual flashes, right? Let's just go ahead and keep using technology because I believe that that is how we're going to get the answers that my labs expects here. So if a pilot is randomly selected, find the probability that he's going to weigh between 120 and 161 pounds, given that the seat was designed for 120-pound passenger or pilots, between 120 and 161. So that's where we're getting these numbers from. But the new mean is 126, and the new standard deviation is 28.8. Second distribution, normal CDF, we want 120 to 161, and we have a mu of 126, a standard deviation of 28.8, and I get 0.4704. It's exactly what they got. And now we're going to have second distribution 2, and we're going to take groups of 39 different pilots. So we're going to divide by the square root of 39, and we get 90 point or 0.9034 when we round to 4 decimal places. So this is 47.04%. This is 90.34%. Which of these is more important? Again, the individual parts are the individual is more important, part A, because the seat performance for a single pilot is important. Whether the ejection seat is going to work or not for that particular pilot. Certain brand of candles has a mean weight of 0.8586 grams and a standard deviation of 0.0524. Those would also be grams. Sample of these candles from a package containing, I'm sorry, I said candles, I meant candies, containing 452 candies, and the package label stated that the net weight is 385.7 grams. If every package has 452 candies, the mean weight of each individual candy must exceed this for the net contents to weigh at least that much. So if one candy is randomly selected, find the probability that it weighs more than that much. Stat, second distribution, normal CDF. So we want more than 0.8533, and we want 1 second EE99. So we want to go to the right. Our mean is going to be 0.8586, and our standard deviation is 0.0524. And we have not the answer that I was expecting. Give me just a second. All right, we're just going to go with this number here, 0.5403, as that's what we should get following the process there. If 452 candies are randomly selected, find the probability that their mean weight is at least this much. So we're going to go back in, and we're going to divide here by the square root of 452. And that gives us an answer of 0.9842. Given these results, does it seem that the candy company is providing customers with the amount claimed on the label? And we would say yes, it does, based off of uh, this number here, right? Because the probability of getting a sample mean of 0.8533 grams or greater when 452 candies are selected is not exceptionally small. Oops, it's not exceptionally small. It's very close to 100%, which is what we want, right? We're saying that there's more than a 98% chance that you get what they advertised or better in the bag. That's really good, actually. So we're gonna stick with that. Just so you know, they got this number, but this number on the answer key was reported as 5398, and that's what I took a second to just stop and see how they got that. I believe what they did was they, let me come back here. I believe they took this z value here of negative 0.10, and they either looked that up in the z table, which I'll go do one of these problems. 0.10 is 4602. And they did 1 minus that, and that's how they came up with 5398. Even though they said they were using technology, I think they used the Z table. This is what you'll get if you use technology, though. So hope that makes sense. Sometimes they're not following their own directions here, and I want you to be able to get the answers. So whereas previously they told us to use the Z table and they used technology, now they're telling us to use technology and they clearly used the Z table. So let's go ahead here and suppose that certain coins have weights that are normally distributed with a mean of 5.515 grams and a standard deviation of 0.078 grams. The vending machine is configured to accept these coins with weights between 5.425 grams and 5.605 grams. If 280 coins are inserted into the vending machine, what is the expected number of rejected coins? Well, let's find the probability of accepting the coins, and then we'll do 1 minus. So lower bound is going to be 5.425. Upper bound is going to be 5.605. Our mean is going to be 5.515. And our standard deviation is going to be 0.078. And we're going to figure that out, and we get 0.7514, and we're going to do 1 minus to find the probability of rejection. So that's going to be 0.2486, and then I'm going to take that times 280, and round to the nearest integer, and I get that I expect 70 of the coins to be rejected. If 280 different coins are inserted into the vending machine, what is the probability that the mean falls between the limits of 5.425 and 5.605. So let's come back here and change this. So now we're talking about the mean value. So we're dividing this by the square root of the 280 coins in our sample. And that makes this probability of the coins on average here being accepted as 1. And so 1 minus that is going to be 0. And they have here 0.9998 when they rounded to 4 decimal places. So they clearly used the Z table here with some rounding for their Z value. So let me show you how they did that. They said that Z is going to be upper bound here is going to be 5.605 minus the 5.515 over 0.078 divided by the square root of 280. So I'm going to type that into my calculator here, 5.605 minus 5.515 over 0.078 divided by the square root of 280. And this is approximately 19.3. And then might need that to 2 decimal places. And then the other one is going to be 5.425 minus 5.515 over 0.078 divided by the square root of 280. And I'm going to just change that one number up there. So that's 5.425. And this is negative 19.3. This is 3.1. And how are they getting these numbers here? They're using their Z table, which again, well, they are telling us to use the Z table here. So if I say bigger than 3.5, they want us to use 0.9999. They want us to subtract off smaller than negative 3.5 is 0.0001. And we get 0.9998. And that's in our region that they say is going to be accepted. And then to get rejection, we do minus that. And that's how they get there like that. And the calculator was just telling us that these numbers are even way smaller than 0.0001. They're so small that they're basically 0, so that this number is basically 100%, and this number is basically 0%, and the difference was basically 1. But we're going to do it the way that we were told to do it here so that we get the right answer in my labs, and they give us an answer of 0.9998. Now, which of these is more significant here? part A, because rejected coins mean lost sales, we don't care about what happens on average. With all 280 coins, we care about each individual coin that's going to be rejected or not rejected. All right, I hope that that all makes sense to you. That is it for this video. Sorry that some of the techniques used didn't match the instructions, but we will come back next time and we will start talking about our topics from chapter 6. See you for the next video.